to make a phosphate buffer, and there's like 20 bottles labeled phosphate. Okay, maybe not 20, but there's a lot of different forms of phosphate, and here's more on which is which, as well as why phosphate is really good for making pH buffers.
Much more detail in a second, but dihydrogen phosphate is referred to as monobasic, and monohydrogen phosphate is referred to as dibasic. You can remember this by remembering that there are kind of 3 oxygens up for grabs in the phosphate groups when it comes to giving and taking protons. If 2 of these have already taken protons, if 2 of these have protons on them, we call it dihydrogen phosphate for those 2 hydrogens. We refer to it as diprotic. It has these 2 groups that can donate protons, or as we call it, act as an acid. And it has this 1 group that can take a proton. And when we say something takes a proton, well, now we're talking about acting as a base. So this is 1 group that can act as a base. So we call it monobasic. And it's got those 2 groups that can act as an acid, so it's diprotic. Now, monohydrogen phosphate, this is going to have 2 of the groups have deprotonated, and thus if something's deprotonated, it can act as a base and take a proton, so it's going to be dibasic. That's these 2 groups that can act as a base, and it has this 1 group that can act as an acid and give a proton, so it's monoprotic, and we can say it's monohydrogen phosphate. Okay, so these are going to be the 2 forms that we're going to be dealing most about. And so why am I not worried about these 2 groups? Well, this has to do with when we look at the pKa's of these groups. And so now we're going to get a little more technical into the chemistry. But the basic idea that we're going to see, and really no pun intended that time, was that this phosphoric acid form and this phosphate form, ion form, are going to be very, very minimal concentrations inside of our cells and inside of our buffers in the lab. And we'll get much more into why this is and how we can actually calculate what proportion of it is each of these species is going to be present at a given pH using something called the Henderson-Hasselbalch equation. But the bottom line is that each acid has something called a pKa, which is the pH at which half of it is going to be the protonated form and half of it is going to be a deprotonated form. So acid and base are really flip sides of the same coin, because if something acts as an acid, it gives up a proton. Well, now it's going to become its conjugate base. And if something is going to accept a proton, well, now it's going to go back and be the conjugate acid. And so why would something be more likely to give or take a proton? Well, this is going to depend on the chemical characteristics of it. And so we'll look a little bit more about these different phosphate forms, while some of them might be more or less likely to give a proton up. Regardless of how likely you are to originally give it up, how likely you are to be able to kind of find a new one if you do give it up, well, this is going to depend on the concentration of those protons available. And if we're talking about the concentrations of protons available, well, now we're talking about the pH. And when we talk about the pH, we have this inverse log scale. What this is going to mean is that if we have a higher pH, that's going to be more basic or alkaline. And it's also going to refer to having a lower concentration of your free protons available. Conversely, if we have a lower pH, that's going to be more acidic. And we're going to have a higher concentration of free protons available. And if you have more free protons available, well, then you're more likely to be in that protonated form, right? So if we go to a low pH, what we're going to have is we're going to be shifting towards this conjugate acid form. So a lower pH is going to shift us towards this conjugate acid form, and a higher pH, fewer protons available, is going to shift us more towards this conjugate base form. And the pKa is going to determine kind of where the halfway mark is. So where do you start going more towards the base, and where do you start going more towards the acid? That's going to be told to us by this pKa. So if we're above the pKa, if we're at a pH that's above the pKa of our acid, what this is going to mean is that there's fewer protons available than the acid would need in order to be half protonated. And so less than half of it is going to be protonated. We're going to have the conjugate base form predominate. If we're at a pH that's below that pKa, well, now we're going to have more protons available. So we're more likely to find it in that conjugate acid form. So if we're at a pH above the pKa, we're more likely to be deprotonated. And if we're at a pH below the pKa, we're more likely to be protonated. And so now let's go back and let's look at the pKa's of these forms of phosphate. Now, if we look at the phosphoric acid, so here's where we have all three of those phosphate groups being protonated. We have a pKa of 2.14. And if we think about our cells in our body being kind of around 7, we're just going to round some numbers here. So we're going to be around 7. Well, the pH is going to be way, way, way above the pKa of phosphoric acid. And remember, if we're above the pKa, there's going to be fewer protons around than it kind of like wants. And so you're going to have it be predominantly deprotonated. And so one of these hydrogen groups is going to deprotonate, giving us this dihydrogen phosphate. And so when we're dealing with this, we're going to have this be predominantly in this direction at our body's pKa, at our body's pH. This is going to be almost entirely in this form when we're talking about going back and forth between these two. But then we have the situation that this can go back and forth with this. And so if we have this going back and forth with this, well, now this is actually going to be more even of a situation because we have a pKa of about 6.86. And if we have a pKa of about 6.86, we're going to have really significant amounts of both of these. And so because we're near that pH, we're going to have we're near the pKa's near our pH, we're going to have relatively even amounts of both of these. Now let's think about what the consequence of that would be. What would happen if you would add a little more acid in there? If you were to add some protons in there, well, now the bases can, those bases take those protons up and kind of bring the pH back to where it was. If you were to add some OH-, if you were to add a base in there, well, now the acid can kind of neutralize that base, maintaining a constant pH. And so this is going to provide really, really great buffering capacity. So something is able to act as a pH buffer to keep the pH constant when the pKa is around that pH. And so we call this like a buffering region, which is kind of like 1 pH unit above or below the pKa. So this one is going to be in that buffering region, as this is why we're going to use these as a buffer in the lab, as well as inside of our cells to maintain that pH at around a 7.4. So it's not just the phosphate ions in there, there are other things too, but this is going to be the key buffering system inside of our cells is going to be this phosphate buffering system. Okay, but we're still not done because we have that one other cell, we have that one other group still. We have this phosphate ion, this PO₄3-. This is also sometimes referred to as orthophosphate. Where ortho is meaning like true. So this is a true phosphate ion. It has all three of these groups deprotonated. Orthophosphate, we call this orthophosphate ion, and it's tribasic because it has those three groups that are able to act as a base and take a proton. And these are really, really likely to do this. So we have a pKa of 12.4. So we're going to have a pKa way above the pH for our that we're normally at. So there's going to be way fewer protons available. There's going to be way more protons available. And so you're going to have these be protonated. And so you're going to have the balance lie towards this one. And so all in all, what this means is that you're going to have a predominance of these two forms. As to why biochemically this might be, well, in each of these cases, what we need to realize is that each of these is going to be kind of equally likely to be protonating or deprotonating. We're just only drawing one of the forms. In the phosphoric acid form, you have that's like 3 chances to deprotonate. And what happens when you deprotonate is a couple of different things. One is that you're going to get this resonance stabilization. So although we're drawing a double bond to this oxygen and a single bond to this oxygen, and the charge on this one, what you really have is resonance going on. And this resonance, basically these electrons or the density is going to be shared between these two groups. And this makes molecules really, really happy when they can do this. So this is going to make this molecule really happy to give up a proton. It's going to easily give up a proton. That's going to be a stronger acid. It's going to have a lower pKa. And when it's also easier for it to give up a proton than these forms, because at this point you're neutral. So molecules like having resonance but they don't like having charge really. And so charge is more easily tolerated if you can share it through resonance, but it's still, molecules would rather not be charged. Like charges repel each other. So if something is already negatively charged, it's going to be hard to add another negative charge. But this is neutral to start with, so it's going to be easier to pull off a proton. We don't have to worry about, to lose a proton, we don't really have to worry about that charge issue as much. So we just get this better stabilization and these three possible groups that can deprotonate. All in all, this is leading to a low pKa. Now, when we have here, well, now we have a negative charge to start with, and we only have two options for which ones can give up a proton. And remember, both of these can be giving up a proton because we have, they're kind of like equivalent because we have resonance between these two groups. When one of these gives up a proton, well, now we're going to be introducing a second negative charge. And remember, the second negative charge, well, now you have two negative charges next to each other. Negative charges are going to be repelling one another, and so that's not going to be very happy. But you're going to get some happiness through the stabilization through resonance once again. So this pKa is going to be pretty reasonable. But now what's going to happen is if you try to introduce a third negative charge, and we have those negative charges being repelling one another, well, this is going to be more complicated, and so you're going to get this higher pKa. And you only have that one possible chance to deprotonate. So overall, you get this higher pKa when we're talking about this. And so this would be the first, this pKa here is referring to the first deprotonation. This would be referring to your second deprotonation, and this would be referring to your third protonation. So in each case, the pKa is going to be referring to just a protonation at one of those single sites. And only this dihydrogen phosphate has a pKa that is around the range that makes it physiologically relevant. At the pH of our bodies, we're going to have very, very little of this because there's too many protons around for it. So we're going to get one of them be protonated. You're going to be predominantly in this acid form. In this case, you're going to have too few protons for this. And so you're going to be deprotonated and you're going to be in this, this conjugate base form. Just a quick note, when we're dealing with these in the lab, what we're often going to see too is that we're going to see these in the salt form. So when we're dealing with like solids and we're weighing out these solids, instead of seeing something that's labeled like dihydrogen phosphate, what we're often going to see is we're going to see something, and we're not going to see something with a negative charge because that negative charge is going to be in a complex. This is an anion. It's going to be in complex with a counter ion, a cation, something that's positively charged, and you get this neutral combination, which we call a salt. So a salt equals plus ion, so that's a cation, and a minus ion, so that's going to be your anion, and you get this neutral combo. Now, in the case of these phosphate groups, they're typically in the lab, we're dealing with them being grouped up with sodium or with phosphate. So what you might see in this case is you have a negative charge of 1, so you would need a positive charge of 1, and this can be given to you through a sodium ion or through a phosphate ion. So what you might see is you might see NaH₂PO₄, or you might see KH₂PO₄, and both of these would be this form. So what about in this case? Well, here you have a negative charge of 2. So in order to neutralize that, you'd need 2 plus charges. And so you can do that by adding two of these cations. So you would have Na2H, we have a single H now, HPO₄, or you would have K2HPO₄. And so these are the forms that you would often see in the lab, and they're also often going to be labeled like monobasic or dibasic. And to remember that monobasic, well, this means that you have one group that can act as a base and take a proton, but kind of a placeholder for the proton, you can kind of think about it, is the cation, that counter ion. So there's going to be one group of that. So it's going to be often a sodium or a potassium. And if you have a dibasic, well, now there's kind of like two groups that are going to be able to take a proton, but right now we have a kind of space holder formed by our metal cations of sodium or potassium. And so that's what you're often going to see in the lab. Okay, so now let's talk about what you would see if you were to actually go inside of those solutions. What would you see inside? And do we really not need to worry about these, what I'm referring to as these minor forms? So this is what we call the Henderson-Hasselbalch equation. And I'm planning to do a video showing you how we can actually derive this equation. But for now, we're just going to use it. And this equation is going to allow us to relate the pH and the pKa and take at a given pH, what proportion is in the acid form or the base form. And if we were to have a given proportion of the acid and the base, what would the pH be? So in this case, we're just going to deal with that first situation. So given a pH, what is the amount of acid and what is the amount of base? So we're going to be dealing with some logarithms. I don't know about you, but I don't really like doing math too much, but this is going to be not too bad. So basically with a logarithm, it's just a different form of writing kind of like an exponential. And I have much more on logarithms in another post, but this is what we're going to be dealing with. And you can also deal with it in your calculator. But a logarithm is basically taking the exponential form and it's putting it in a different form and asking how many times you have to multiply b by itself to get a. And in this case, we're dealing with a log of 10. So our b is going to be 10. And another thing to know is that when we take the negative log 10 of something, then we're going to say that's going to be notated by a p. So a p is going to be the negative log 10 of something. And so that's how we get pH from this proton concentration, is by taking this negative log 10. And in the case of our pKa, this is comes from taking the negative log 10 of our acid of our conjugate base over our conjugate acid and the protons. So much more in this when I'm gonna do my post deriving that Henderson-Hasselbalch equation. But just know that in order to undo a log 10, we take the anti-log 10. And you can do this with your calculator. And it's also going to basically refer to going 10 to the value. And so if you had take an anti-log of 2, well, this is going to give you 10 to 2, which is going to be 100. And in fact, if we look at the pKa relative to the pH, we see that for each increase in pH above the pKa we're going to have 10-fold less of the protonated form. And for each pH unit below the pKa, we're going to have 10 times more of the acidic form. And so if we're at the pKa, we're going to have equal numbers of both. But we can see that as we move away from that pKa, we're quickly going to deplete the amount of acid or base, depending on which direction that we go. So we'll start with just like an estimate, and then we'll go into actual calculations. So when we look at our phosphate buffers, if we're at a pH of 6.86, and now let's consider a pH of about 7.4. We're going to be about 1 pH unit below the pK, 1 pH unit above the pKa. So basically, we're going to have a little fewer protons available. We're going to have about 10-fold more of that base form. And so we're going to have about 9% of it be protonated. And so it's not quite equal numbers of these two, but it's going to still be significant amounts of each of these. And so you'll have significant buffering capacity. But now what's going to happen if we go to if we consider something that is going to be a stronger acid? If we consider this phosphoric acid, which has a pKa of 2.14. So now at a pH of about 7, so we're going to have way fewer protons than we'd actually need to be half protonated. And it goes actually above this line. But if you were to imagine you have +5, well, now you're going to have 100,000 over here, and 0.001% is going to be in the acid form. And so you're going to have it be predominantly in this conjugate base form. And so you're going to have like 99.999% in this conjugate base form. And so that's why we don't really need to worry about this form. We're going to have it mostly in this form, in this conjugate base form of phosphoric acid. But remember that this is going to be the conjugate acid form of this reaction. So dihydrogen phosphate This is the conjugate acid of monohydrogen phosphate, but it is the conjugate base of phosphoric acid. But we don't really need to worry about the phosphoric acid because it's almost always going to deprotonate to give us this dihydrogen phosphate. Okay, so now what about this, this monohydrogen phosphate? So remember, this is the conjugate base of this dihydrogen phosphate. Now it has a pKa of 12.4. So at a pH of about 7.4, well, now we're actually going to be below the pKa. So we're going to be about 5 units below the pKa. And so once again, if I go extend my scale, we're going to have 100,000-fold more of the acid than the base. And we're going to have about 99.999% of it be protonated. And so when we're talking about it being protonated, it's going to be in the conjugate acid form. And so we're going to be dealing with this form, this monohydrogen phosphate form, when it comes to this equilibrium. Okay, so that was kind of just estimating it. But now let's actually show how we can solve this using the Henderson-Hasselbalch equation for any given pH and any given pKa. We'll consider a pH of about 7.4, and then look at the pKa's of each of these. So let's start with this, let's start with our main one that we're dealing with, this dihydrogen phosphate, monohydrogen phosphate equilibrium, where our pKa is 6.86. So we have our pH is going to be 7.4 equals 6.86 plus log 10 of our free acid over our free base. So we don't know the actual concentrations here. I haven't given you like the molarity. So we're just going to worry about this ratio of the two. And if we do the math, basically we subtract 6.86 from either side. What we're going to get is 0.54 equals the log 10 of this value. We're just going to call it x because we're looking at the ratio here. And so in order to reverse this, we're going to take the anti-log. So x is going to be the anti-log of 0.54, which is basically saying x is 10 to the 0.54. And so if we do this on our calculator, what we can find is that we get 3.47. So we're going to have about 3.5-fold more of our conjugate base as our conjugate acid, but we're still going to have pretty equal amounts of both. And if we knew the concentration, we could put actual molarity values into this to find out the molarity of the acid and the base forms. Okay, now let's look at the phosphoric acid form. Here, if we take that same pH, but we take a pKa of 2.14, and then we're going to do our log 10, and again, we're just going to call this value x that we're going to solve for. Now, in this case, if we subtract 2.14 from each side, we're going to get 5.26 is going to equal log 10 of x. And again, if we take the anti-log of 5.26, well, now what we're going to get is we are going to get 181,970. So we're going to have way more of it be in that conjugate base form than in the conjugate acid form. We're going to have about 182,000 times more. So yeah, a lot. Okay, finally, let's go and let's look at this fourth case. And so this fourth case, we're talking about the monohydrogen phosphate deprotonating. Now in this case, we start with that same pH, but here we're going to have 12.4. And again, we're going to have the log 10 of x. And when we do the math, same as before, this case, we're going to do 7.4 minus 12.4, about -5. And if we take 10 to the -5, we're going to get 0.00001. And in fact, if we were to go back and look at our chart, we can see Well, here it is written a little backwards because here it's in terms of protonated. But if we were to take it in the other direction, we could see that we would be getting 0.001 if we were to go out to the 5 like we did before, but I just had written it on my other slides. So we really don't need to worry about those other forms when we're talking about what's happening at a pH of about 7.4, a pH about 7, anywhere around that. Our predominant forms are really going to be these two forms that I have highlighted here. And so when you go to the lab to make a buffer, you're going to be mixing these two forms. And the amount of each that you're going to add, we can use that same Henderson-Hasselbalch equation to actually tell us how much we need to add of each of those in order to get to a desired pH. And so we use that same equation to figure out the ratio of each of these we need, and then we'll calculate, we can then multiply that by a molarity that we want in order to figure out how much of each of these we need to add, given the molecular weights of each of them. And so I'll probably do a video in the future about how we can actually do those calculations. But for now, just know that you can. And also know that in the lab, when we're dealing with this, you're typically going to be dealing with a salt form. So you're going to be dealing with, if you're going to be dealing with the acid form, this is going to be your dihydrogen phosphate. It'll typically be in the form of something such as a sodium dihydrogen phosphate or a potassium dihydrogen phosphate. The bottle might also be called, say it's monobasic, because remember, 2 of the groups are protonated. And one of the groups is deprotonated, able to act as a base. But here it's going to be we're going to be focusing on its use as an acid. So it's diprotic, and you can think about those protons like that one spot that's available to protonate this monobasic spot. Basically, it's going to be taken, a placeholder is going to be this cation, this sodium, or this potassium. Now, the base form that you're going to add is going to be your monohydrogen phosphate, which you're going to see up on the bottle. This is going to be like Na2HPO₄ or Ka2 or K2HPO₄, so sodium, disodium phosphate, or dipotassium phosphate. And this is often going to be called dibasic because it has these 2 spots that are going to be able to take a proton, but right now they're being neutralized by the cation provided by the salt. And it has this one group that can act as an acid, so that's monoprotic, but it's very unlikely to act as an acid. It's very unwilling to act as an acid, and so at the pH we're dealing with, we're going to see predominantly in this form. Now, if you were to mix equal amounts of each of these, you would get a pH of
6.86.
If you wanted a pH that was a little lower, where we want more acid, we're going to add more of this acid form. And if we want a pH that's higher, we're going to add more of the base form. And the exact amount that we'll need to add, well, this is something that we can calculate using that Henderson-Hasselbalch equation. And so you'll often see in the lab, in your classes, you're going to be required to actually calculate how much of these to mix in order to make a buffer, or what the pH would be if you mix certain amounts of each. So hope this video helped you understand what these different forms of phosphates are and why we call them the different things. And best of luck with your calculations.